Good morning, friends. In chapter 12, atoms, already we discussed the most of the numerical of illustration and exercise. Now the one remaining numerical of exercise 12.9. This is the quite lengthy, due to that reason we skip it. Okay, now here the 12.5 electron volt electron beam is used to bombard the gaseous hydrogen at room temperature. What series of wavelength will be emitted? In gaseous hydrogen atom, when the electron beam of 12.5 electron volt is bombarded, so what series of wavelength will be emitted? We have to find out the series and also what is the wavelength of the spectral light. Okay. Now we know that the ground state energy of hydrogen atom at room temperature is minus 13.6 electron volt. Ground state energy of hydrogen atom at room temperature is minus 13.6 electron volt. Right? Now, the electron beam, when an electron beam of or the electron beam is used to bombard on a gaseous hydrogen, its energy becomes equal to, already the minus 13.6 electron volt is already have. Now this energy is added to the hydrogen gas. That is the 12.5 electron volt. Therefore, the total energy is minus 1.15 electron volt is emitted. 1.1 electron volt. Right. Therefore, what is the energy in nth orbit? Now, energy in nth orbit. Now listen, when at room temperature, when the electron is in ground state in hydrogen atom, it has the 13.6 electron volt energy. When the electron beam of energy 12.5 electron volt is bombarded on this hydrogen atom, so what's happened? This electron absorb the energy and get excited. Excited to what are the energy level? We are interested to find out up to the which energy level or the which orbit the electron is excited. Therefore, energy in nth orbit is En is equal to minus 13.6 upon n square electron volt. But after the bombardment of the electron beam, the energy of the gaseous hydrogen is minus 1.1 electron volt. Therefore, minus 1.1 electron volt is equal to minus 13.6 upon n square electron volt. Therefore, n square is equal to 13.6 upon 1.1. Right? 13.6. Right? So is equal to divided by 1.1, therefore 12.36, and therefore n is equal to 3.51. Therefore the possible orbit is 3. Therefore possible orbit is n is equal to 3. That means after the electron beam is bombarded on a gaseous hydrogen, the electron in hydrogen atom already at room temperature is in ground state. Now these electrons are excited to the third orbit. Therefore, the energy levels like this way. There is the n is equal to 1 ground state, n is equal to 2 first excited, and there is the second excited state. Here the energy is minus 13.6 electron volt. Here the energy is 13.6 minus 3.4 electron volt. And here minus 1.51 electron. Therefore, the transition of electron takes place from n is equal to 3 to n is equal to 1. Second possible transition is n is equal to 2 to 1, and third is 3 to 2. Corresponding to these two transitions, Lyman says is obtained. Here alpha line, here beta. Corresponding to this transition, here the Balmer series is obtained. Here the closest transition, therefore alpha line is obtained. Alpha line is obtained. Therefore, the spectral line of emission spectra are Therefore, spectral lines of emission spectra are is equal to n into n minus 1 by 2. n is equal to 3. Therefore, 3 into 3 minus 1 by 2. Therefore, the three spectral lines are obtained. Therefore, the three spectral lines are obtained. Corresponding to the 3 to 1 transition, 2 to 1 transition, and third corresponding to the n is equal to 3 to n is equal to 2 transition. Clear it? Okay. Again, we repeat it. The ground state energy of the hydrogen atom at room temperature is minus 13.6 electron volt. Yeah, that is the initial condition. When the electron beam is used to bombard on gaseous hydrogen, its energy becomes, already the hydrogen atom has the energy is minus 13.6. Due to the bombardment of electron beam, it gains the energy 12.5 electron volt. Therefore, its energy becomes 1.1 electron volt. Therefore, due to the increase in energy, so electron is excited to whatever the state. Therefore, now energy in nth orbit is En is equal to minus 13.6 upon n square electron volt. En is now 1.1 minus 1.1 electron volt is equal to minus 13.6 upon n square. So thus we obtain the value of n is 3.51. Therefore, the possible orbit is n is equal to 3. That means the electrons from ground state after bombardment of the electron beam are excited to the third orbit or the third level. So after the electron excited to the third level, so how many spectral lines are possible? Therefore, the spectral line of emission spectra are n into n minus 1 upon 2 is equal to n is equal to 3. Therefore, 3 into 3 minus 1 upon 2. Therefore, the three spectral lines are possible. Corresponding to the transition of electron from third orbit to the first. Second line is corresponding to the 2 to 1. And third line corresponding to the 3 to n is equal to 2. Now, when the electron makes the transition from 3 to 1 and 2 to 1, so Lyman series is obtained, and alpha line and beta line of Lyman series are obtained. Now, corresponding to the transition of electron from third orbit to the second orbit, the second series, that means the Balmer series, is obtained. Here the closest transition, therefore alpha line of the Balmer series is obtained. We are interested to calculate the wavelength of this series or this spectral line. Therefore, in transition from n is equal to 3 to n is equal to 1, n is equal to, right, and n is equal to 2 to n is equal to 1. Two lines of Lyman says, two lines of Lyman says, and in transition from n is equal to 3 to n is equal to 2, n is equal to 2. One line of Babar says, one line of Babar says are okay. So the transition from n is equal to 3 to 1 and 2 to 1. The two line of Lyman says and transition of electron from 3 to 2, one line of Babar says are okay. Right? In transition from n is equal to 3 to n is equal to 1, n is equal to 3 to n is equal to 1. The beta line of, or the wavelength of beta line of Lyman says is okay, and that wavelength is lambda 31 is equal to hc upon E1 minus E3. Hc, H Planck's constant 6.625 into 10 is to minus 34. C, 10 into 10 is to 8 upon E1. E1 is, what is the energy? Minus 13.6 minus 3.4. Electron volt convert into joule. Therefore, 1.6 into 10 is to minus 19. So as we simplify it, so we obtain 103 nanometer. That is the wavelength of H alpha line for the Lyman says 103 nanometer. Now, in transition from n is equal to 2 to n is equal to 1. The wavelength of alpha line of Lyman says is emitted. Therefore, we can write lambda 21. Lambda 21 is C upon E1 minus E. E1 minus E. Therefore, Hc upon E1. E1 is minus 13.6 minus E1 minus E2. Here E3 1.51, just 1.51. And here the minus 13.6 minus 3.4. Also multiply with the charge of an electron, convert into the joule. 10 is to minus 90. Thus we obtain the 122 into 10 is to minus 9 meter. That means the 122 nanometer. 122 nanometer. That is the wavelength of alpha line 4. Lyman says 122 nanometer. There is the beta line for Lyman says, that is the alpha line for the Lyman says. Again, here we find out the number of the how many spectral line obtained? 3. This 3 spectral line corresponding to the when the electron make the transition from 3 to 1, and second 2 to 1, and third spectral line corresponding to the 3 to 2. Right? Okay. In transition from 3 to n is equal to 1 and n is equal to 2 to 1, the two lines of the Lyman says and one lines of corresponding to the n is equal to 3 to n is equal to 2 transition, one line of Balmer says are obtained. Now in transition from n is equal to 3 to n is equal to 1, the wavelength of beta line of Lyman says is emitted for the octave. Therefore, lambda 31 is c upon E1 minus E3. H Planck's constant, c velocity of light, E1 is minus 13.6, E3 minus 1.5. Denominator term is in electron volt, we have to convert into joule, therefore multiply with the 1.6 into 10 raised to minus 90. If we simplify this, so we obtain 103 into 10 raised to minus 9, that means the 103 nanometer. That is the wavelength of beta line in Lyman says, and in transition from n is equal to 2 to n is equal to 1, the wavelength of alpha line of Lyman says is emitted. How we calculate the wavelength of alpha line of Lyman says? Lambda 21 is equal to hc upon E1 minus E2. hc upon E1 minus 13.6 minus E2 minus 3.4. Therefore, if we simplify, we obtain 122 nanometer. Now the third transition, in transition from n is equal to 3 to n is equal to 2. The wavelength of alpha line of Balmer says is immediate. Therefore, lambda 32 is equal to hc upon E2 minus E3. E2 minus E3. Substitute the value of h 6.625 10 is to minus 34 c 3 into 10 is to 8 upon minus E2. E2 is minus 3.4 minus 1.51. That is in electron volt, convert into joule, 1.6 into 10 is to minus 19. As is simplified, we obtain the 657 into 10 is to minus 9 meter. That means 657 nanometer. That is the wavelength of alpha line of Balmer says. So here the 3 spectral lines corresponding to this value, 2 of Lyman says and 1 of the Balmer says are obtained when the electron beam of the energy 12.5 electron volt is bombarded on the gaseous hydrogen. The wavelength of these 3 lines, beta line, alpha line of Lyman, and there is alpha line of Balmer says. Right? Balmer says. So it is numerical but quite lengthy. Clear? After the completion of numerical of illustration and exercise, already all the numerical of additional exercise are cancelled for the board exam. But you consider the 2 numerical possible to ask in competitive exam. One is the 12.15 and next is the 12.17. 12.15 is the total energy of an electron in the first excited state of hydrogen atom is about minus 3.4 electron volt. What is the kinetic energy of the electron in this state and potential energy of the electron in this state? That means we have to find out the kinetic energy and potential energy of an electron in second orbit or second energy state or in first excited state. For that purpose, we know that from Bohr's hypothesis, the angular momentum is equal to integral multiple of h upon 2 pi. From Bohr's hypothesis, MVR is equal to NH upon 2 pi. Right? And also we know that centripetal force is equal to Coulomb force exerted by the nucleus on the electron. Therefore, centripetal force mv square upon r is equal to Coulombian force of attraction is square upon 4 pi epsilon 0 r square. For H atom, Z is equal to 1. Z is equal to 1. 1 times R cancel. Therefore, kinetic energy is equal to half mv square is equal to square upon 8 pi epsilon 0 r. Listen here, we multiply both sides by half. Therefore, half mv square is the kinetic energy of electron. So is equal to square upon multiply by 2 of denominator term. Therefore, 8 pi epsilon 0 into r. Therefore, kinetic energy is square upon 8 pi epsilon 0 r. And potential energy is equal to U is equal to minus square upon 4 pi epsilon 0 into 4 pi epsilon 0 into r. Right? Okay. Therefore, the potential energy is equal to minus. Now, instead of the square, so we multiply and divide it by 2 of this equation. Therefore, square upon 8 pi epsilon 0 r. So, from this equation is equal to kinetic energy. Therefore, potential energy is minus 2 times of kinetic energy. Again, the potential energy is this minus square upon 4 pi epsilon 0. But the equation of kinetic energy is square upon 8 pi epsilon 0. Then the difference is this 8 into 4. So as we multiply and divided the right hand side of equation of potential energy, therefore minus 2 is square upon 8 pi epsilon 0 r. So this term is square upon 8 pi epsilon 0 r is our key. Therefore minus 2. Therefore the potential energy is minus 2. Therefore total energy of an electron is the addition of kinetic energy and potential energy. E is equal to K plus E. Kinetic energy is K, but potential energy is minus 2K. Therefore, total energy is minus K. Negative of kinetic energy. Now listen here. First, we are interested to find out the kinetic energy. Total energy in first excited state is minus 3.4. In first excited state, E is equal to minus 3.4 electron volt. Therefore, K is equal to minus E is equal to minus into bracket minus 3.4 is equal to 3.4 electron volt. There is the kinetic energy of electron in first excited state. Second is potential energy in first excited state. U is equal to minus 2K. U is equal to minus 2. Therefore, minus 2 into 3.4. So is equal to minus 6.8 electron volt is the potential energy of an electron in first excited state. So now here, what are the relations we obtained? That is the most important for the concept of MCQ type question. Potential energy is twice of the kinetic energy. Kinetic energy is equal to the total energy, but negative. Again, from Bohr's hypothesis, LBI is equal to NH upon 2 pi, and centripetal force is equal to Coulomb force. Therefore, mv square upon r is equal to e square upon 4 pi epsilon 0 r square. 1 times r cancel. Multiply both sides by half. So left hand side becomes the kinetic energy. Therefore, kinetic energy is equal to half mv square is equal to e square upon multiply by 2 8 pi epsilon 0 r. So that is our equation of kinetic energy. Now potential energy E is equal to minus e square upon 4 pi epsilon 0. Yes, we multiply the right hand side of this equation by 2. 2 upon 2. Therefore, minus 2 into bracket e square upon 8 pi epsilon 0 upon r. But this is equal to kinetic energy. Therefore, potential energy is minus 2k. Now the total energy of an electron E is equal to addition of kinetic energy plus potential energy. Therefore, Km plus into bracket minus 2k. Therefore, E is equal to minus k. Now, in first excited state of the hydrogen atom, the total energy is given, that is the minus 3.4. Therefore, kinetic energy is equal to minus E. Therefore, minus of minus 3.4. Therefore, 3.4 electron volt energy is the kinetic energy of electron in first excited state of hydrogen atom. Now, the potential energy is in first excited state. So U is equal to minus 2k, but the k is equal to 3.4. Therefore, minus 2 into 3.4, it means minus 6.8 electron volt. Clear it? Okay. After that, the next numerical 12.17. Obtain the first Bohr's radius and ground state energy of muonic hydrogen atom. Muonic hydrogen atom, that means an atom in which the negatively charged muon, mu minus, of mass about 207 MeV. That means the muon is heavier than the electron by 207 times. So 207 into mass of an electron. This muon are revolved around the proton in muonic atom. Again, obtain the first Bohr's radius and ground state energy of muonic hydrogen atom. Now we know that from Bohr's hypothesis, if the electron revolves in the orbit of radius r, the radius r is equal to Bohr's atomic model. If electron revolve in orbit of radius r is, then radius r is equal to n square h square epsilon 0 upon m pi square. So from this equation, this term are constant. Therefore, radius is inversely proportional to the mass of the atom. Therefore, radius is inversely proportional to the mass of atom. Therefore, the radius of muonic atom R mu to the radius of electronic atom Re is equal to Me upon Mu. From this equation, R mu is equal to Re That means the radius of electric atom into Me upon 207 times of Me cancel. Radius of electron atom is the Bohr's radius. Already we know that there is a 5.3 into 10 is to minus 11 or 0.53 into 10 is to minus 10. Therefore, radius of Munich atom R mu is equal to 0.53 into 10 is to minus 10 upon 207. Upon 207. That means 2.56 into 10 is to minus 10 meter. That is the Bohr radius for Munich atom. First Bohr's radius for Munich atom. Now we are interested to find out the ground state energy of Munich atom. For that purpose, the energy of electron. Now, energy of an electron in orbit of radius r is now the energy of electron in orbit of radius r is the energy E is equal to minus Me is to 4 for hydrogen atom we are discussing upon 8 epsilon 0 square n square h square. Now for given to electron atom and Munich atom, these terms are constant. Therefore, energy is directly proportional to the negative of mass. Negative of mass is directly proportional to the minus M. Therefore, energy of Munich atom to the energy of electronic atom, to the electron atom, is equal to mu upon Me. Therefore, the energy of Munich atom is equal to E mu upon M. So is equal to E, here the 207 times Me upon Me. Me cancel. E, already we know that the ground state energy of the hydrogen atom is minus 13.6 electron volt into 207. Therefore, 2.81 into 10 is to 3 electron volt. That is the negative. So it's equal to minus 2.81 kilo electron volt. That is the energy of ground state of Munich hydrogen atom. Again, the example is very easy, but here the atom is given the Munich. That means in hydrogen atom, in proton is center, while the electron are revolved around the nucleus in ground state and other orbit. That is the electron atom. And Munich atom, at nucleus the proton are present, while the muon, mu minus r, revolve in the orbit. Here we know that the first Bohr radius and ground state energy of the hydrogen atom. Here we have to find out what is the radius, Bohr's radius, and what is the ground state energy of Munich hydrogen atom. For that purpose, we are using the Bohr's atomic model. If the electron evolve in orbit of radius r, then the radius r is equal to n square epsilon 0 upon m pi square. Therefore, r radius is inversely proportional to the mass. So, using this concept, ratio of radius of Munich atom to the our hydrogen atom, Me upon Mu. Therefore, R mu is equal to Re into Me upon 207 Me cancel. Re is our first Bohr radius. R0 the radius 0. We know it, the value 0.53 into 10 is to minus 10 upon 207. Therefore, 2.56 into 10⁻⁻10 atom. Right? That is the first Bohr radius of muonic atom. Now, the energy of an electron in orbit of radius r is E is equal to minus m⁴ upon 8 epsilon 0 n square square. So this part is constant, therefore energy is directly proportional to the minus m. Therefore the ratio of energy of muonic atom to the our original hydrogen atom is equal to mu upon me. E mu is equal to E mu upon me. E, that is the energy of hydrogen atom in ground state. Here mu 207 times me upon me cancel. Therefore 207 times energy of ground state in hydrogen atom. The energy of hydrogen atom in ground state minus 13.6 electron volt. Multiply it 207, so we obtain minus 2.81 into 10⁻³ electron volt. Therefore, the energy of ground state of muonic atom is 2.81 minus 2.81 kilo electron volt. Here chapter 12 is complete. Right? Okay.